Welcome back, generals, to another Let's Fix Generals Zero Hour to make the best game ever. Okay, so last session, I think we pretty much determined that we probably need to roll our own interpretation of the MachO symbols, because there is no single project that gives us all we need likely out of the box. So we probably need to do this ourselves. So last session I've asked ChatGPT about some references. Okay, so this runtime architecture, what about this one? Let's take a look at it, see what's in there. MachO runtime architecture. Is it this one? Oh, retire document. There's a link here. Let's copy the link. Put it here. Okay, this can't be found. MachO runtime. Yeah, but it's probably MachO runtime. I don't know. Maybe it's this or maybe not. Well, we can look through this, see what's in here. Okay, it's a native executable format of binaries in OS X, and it's a preferred format for shipping code. Executable format determines the order in which the code and data in the binary file read into memory. The ordering of code and data has implications for memory usage and paging activity, and thus directly affects the performance of your program. MachO binary is organized into segments. Each segment contains one or more sections. Oh, okay, so there are child sections. No. A segment contains sections. Okay. Code or data of different types goes into each section. Segments always start on a page boundary, but sections are not necessarily page aligned. Okay. A page is typically like 4 kilobyte, for example. It can be different. The size of a segment is measured by the number of bytes. The size of a segment is measured by the number of bytes in all the sections it contains, and rounded up to the next virtual memory page boundary. Okay, makes sense. A segment is always a multiple of 4 kilobytes. Okay, 4 kilobytes, with 4 kilobytes being the minimum size. Okay, so it can be larger than this. Yeah. It doesn't matter. The segments and sections of a MachO executable are named according to their intended use. The convention of segments names, all uppercase letters, precedes by double underscores. The convention for section names is to use all lowercase letters preceded by double underscores. Okay. There are several possible segments within a MachO executable, but only 2 of them are of interest in relation to performance. Yeah, because it's a runtime. So text is all the executable instructions, all the functions, and data is all the static data. That is all the static data initialized with. Yeah, like variables and all static data, variables, strings. Yeah. Okay, text segment, read-only area containing executable code and constant data. Constant data, what does that mean? By convention, the compiler tools create every executable file with at least one read-only text segment, at least. Because the segment is read-only, the kernel can map the text segment directly from the executable into memory just once. When the segment is mapped into memory, it can be shared among all processes interested in its contents. This is primarily the case with frameworks and other shared libraries. The read-only attribute also means the pages that made up the text section never have to be saved to backing store. To be saved to backing store. I don't know what that means. I don't know. Backing store? Maybe something OS X specific. If the kernel needs to free up physical memory, it can discard one or more text pages and reread them from disk when they are needed. Okay, I see. It lists some of the more important sections that can appear in a text segment. For a complete list, see the MachO runtime architecture. Where's that? That's the same thing here. Where's that? MachO runtime architecture. Uh-huh. Okay. Uh-huh. Mm-hmm. We will look at that next. Mm-hmm. Okay, let's bookmark this thing here. And this one as well. Let's read it all. Well, the interesting parts. Okay, the sum of the important text section that can appear in a text segment from complete list of segments. See this? Yeah, okay, so there's a text. So these are the sections in the segments. A compiled machine code for the executable. The general constant data. General constant data. Huh, I thought that this would be in a data section actually. Here in this one. C string, literal string constants. Okay. Okay. I also thought that these would be in the data section. And pick symbol stub, position independent code stub routines used by the dynamic linker. Okay. Data segment, read write. The data segment contains the non-constant data for an executable. Non-constant data. This segment is both readable. Ah, okay, so this is for statics that are not const, that can mutate over the lifetime. Okay, interesting. I thought that this would be like, I don't know, allocated on runtime and wouldn't be like a data segment. Because why would it need to be? Why couldn't you just allocate it? Maybe because it statically refers to these things in the executable and it's not a runtime address. Yeah, maybe that's why. Like it needs a fixed address, so like something refers to static data with a fixed address in the data segment, right? So it needs to live there. Maybe that's why. The data segment contains non-static data for an executable. The segment is both readable and writable. Because it is writable, the data segment of a framework or other shared library is logically copied for each process linking with the library. Logically copied. Okay. When memory pages are readable and writable, the kernel marks them copy on write. This technique defers copying the page until one of the processes sharing that page attempts to write to it. When that happens, the kernel creates a private copy of the page for that process. The data segment has a number of sections, some of which are used only by the dynamic linker. Table 2 lists blah blah blah. Okay, for let's see this. Okay. Data initialize global variables int a static. Wait, hold on. Why is this a global? When it's outside of a function. Okay. Yeah. So if you have like a CPP file and you put in an int a1 in a global scope outside of a function, then this would be a data. Yeah, okay. And the data refers to, so basically there will be a 4 byte in the data segment and it's initialized with 1. Yeah. Constant data needing relocation. Const char p foo. Constant. Well, what this is, constant data needing relocation. But okay. So the pointer is is not mutable, right? The const here says that this pointer cannot be changed, but this could be modified. The string that it points to can be modified, but it needs to reference this. So this string lives in here, right? So this points to an address in here. Okay. BSS, uninitialized static variables, uninitialized. Okay. Uninitialized external globals, outside function blocks. So that means if like if you look at a symbol and if we look at a symbol and we don't really know like what the symbol actually refers to, we can look in which section is it. Is it here in common or is it in cons? And then this tells us what this symbol actually is, right? So this one tells us it's an uninitialized external global, right? Okay, that is useful information. DYLD, a placeholder section used by the dynamic linker. Placeholder section. Lazy symbol pointers. Symbol pointers for each undefined function called by the executable. Undefined function. For each undefined function. Non-lazy symbol pointers. Symbol pointers for each undefined data symbol referenced by the executable. I don't know what that means. MachO performance implications. The composition of the text and data segments of a MachO executable file has a direct bearing on performance. Okay. The techniques and goals for optimizing these segments are different. However, they have a common goal: greater efficiency in the use of memory. Yeah. Most of the typical MachO file consists of executable code which occupies the text sections. The text sections is read-only and is mapped directly to the executable file. Thus, if the kernel needs to reclaim the physical memory occupied by some text pages, it does not have to save the pages to backing store and page them in later. Does not have to save them because it's simply just reading from the file on disk and it's just there, right? It only needs to free up the memory, and when the code is later referred, read it back from this. Yeah, makes sense. Also, this is cheaper than swapping because it involves one disk access instead of two. It can still be expensive, especially if many pages have to be recreated from disk. One way to improve the situation is through improving your code's locality of reference. Locality of reference. Okay, we don't care about this. Unlike the text segments, the data segment can be written to, and thus a page of the data segment are not shareable. Yeah, because it's process local. Oops, I didn't mean to click that. The non-constant global variables in frameworks can have an impact on performance because each process that links with the framework gets its own copy of these variables. The main solution to this problem is to move as many of the non-constant global variables as possible to the non-constant global variables as possible. Non-constant to the text const section by declaring them const. Because they are immutable, then, yeah. Reducing shared memory pages describes this and related techniques. This is not usually a problem for applications because the data section in an application is not shared with other applications. The compiler stores different types of non-constant global data in different sections of the data segment. These types of data are initialized static data and symbols consistent with the ANSI notation and are declared extern. Initialized static data is in the BSS section. Aren't declared. Wait, hold on. Right, so it's in this one here, yeah. Tentative common. Tentative definition symbols are in the common section. External globals. Okay, the ANSI and C++ standard specify that the system must set uninitialized static variables to 0. The system must set uninitialized static variables to 0. Oh, is that true? I didn't know that. That's interesting. The system must set uninitialized static variables to 0. Huh. I thought they would just remain uninitialized. Other types of initialized data are left uninitialized. What does that mean? What other types? The system must set uninitialized static variables to 0. Because uninitialized static variables and tentative definition symbols are stored in separate sections, the system needs to treat them differently. But when variables are in different sections, they are more likely to end up on different memory pages, and those can be swapped in and out separately, making your code run slower. The solution to these problems, as described in Reducing Shared Memory Pages, is to consolidate the non-constant global data in one section of the data segment. Okay, well, these are details. We don't care about this. Okay, but this is good to know. And this as well. Why can't we close this here? What is this bullshit? Okay. Managing code size. Do we care about this? No. We don't care about optimization. Avoid excessive function inlining. Although inline functions can improve speed in some situations, they can also degrade performance if used excessively. Inline functions eliminate the overhead of calling a function, but do so by replacing each function call with a copy of the code. If an inline function is called frequently, this extra code can up quickly, bloating your executable and causing paging problems. Basically, it just makes the code enormously bigger. Yeah. Used properly, inline functions can save time and have a minimal impact on your code footprints. Remember that the code for inline functions should generally be very short and called infrequently. If the time it takes to execute the code in a function is less than the time it takes to call the function, if the time it takes to execute the function, the code in the function is less than the time it takes to call the function, yeah, the function is a good candidate for inlining, yeah, because essentially you would waste time with all this calling, and the function then maybe just like has one instruction inside, and that's not very, not very efficient, yeah. Generally, this means that an inline function probably should have no more than a few lines of code. You should also make sure that the function is called from a few places as possible in your code. Even a short function can cause excessive bloat if it is made inline in dozens or hundreds of places. Okay, but nowadays, at least with MSVC, inlining is pretty much automated, so the compiler makes a choice of where inlining takes place. And even if you drop the inline keyword, it's just a recommendation. Apart from force inline, that will force inline. Okay, I think, what about this? Improving locality of reference. Okay, we don't care. Order files. We don't care. We don't care. We don't care. This is all optimizations for the runtime. Don't care. Okay, what about this? Reducing shared memory pages. Declare as cons, yeah. Remember the mark point is as constant. Yeah, the const needs to be here. Okay, this is actually useful information here. Down here. So the goal of merging BSS and data sections is to reduce the number of memory pages used by your application. If moving data into the data section increases the number of memory pages in that section, there's no benefit to this technique. Adding to the pages in the data section increases the amount of time spent reading and initializing that data at launch time. Suppose you declare the following static variables: static int, x, static short, and an array. To move these variables into the data section of your executable's data segment, you would change the definition to the following. Initialize. Wait, where is it before? So it's in a BSS before, what? If I'm not mistaken, let me double check. BSS was uninitialized static variables. Okay. Yeah. But what's the downside of having it in the BSS? Ah, that is like in different locality. To move these variables into the data section of executables data segment, you would change the definition to the following. Okay, I understand. So you probably want to, like, if you have statics, in your executable, and they are used by functions in one go, then you probably want them to be you probably want them to be a nearby, so bundled together in the BSS or in the data section. So if some of them would be uninitialized but many others are initialized, then maybe it makes sense to just initialize all of them so they are all bundled together in the data section instead of being spread over the BSS and data section, which likely will have quite a little bit of space between them, right? And so when then a function needs to like read this, then it needs to read from this and from this. So it's like two accesses to different memory pages. And then that is more expensive than accessing one memory page, right? Because yeah, you need to load it in L3 cache, and then it needs to go up the caches. And so, yeah, the less memory you touch, the faster it is, right? Tentative definition symbols. The compiler puts any duplicate symbols it encounters in the comments section of the data segment. Duplicate symbols. How can there be duplicate symbols? The problem here is the same as with uninitialized static variables. If an executable non-constant global data is distributed among several sections, it is more likely that this data will be on different memory pages. Yeah. Consequently, the pages may have to be swapped in and out separately. The goal for the comment section is the same as for the BSS section, to eliminate it from your executable if you have a small amount of data in it. Okay, I'm not sure I understand this. A common source of tentative definition symbol is the definition of the symbol in a header file. Tentative definition symbol. Typically, headers declare a symbol, but do not include the definition of that symbol. Declare a symbol, yeah, but do not include the definition. Okay, yeah. The definition is instead provided in an implementation file, so the CPP file. But definitions appearing in header files can result in that code or data appearing in every implementation file that includes header file. The solution to this problem is to ensure that header files contain only declarations, not definitions. For functions, you would obviously declare a prototype for that function in your header file and put the definition of the function in your implementation file. For global variables and data structures, you should do something similar. Rather than defining the variable in your header file, defining means like that's where it exists, so it's not the declaration. Define it in your implementation file and initialize it appropriately. Then declare the variable in your header file. Preceding the declaration with the extern keyword. Is this necessary though? Do you actually need to make it extern? For functions, you don't need to do that. I wonder what happens if you omit this extern actually. Extern versus no extern. What is the difference? Extern in global variable. So what happens if we omit this extern keyword and we just have this here? So it's still a declaration and the definition would be in the C file. I'm not sure if it on variables would incur a compile error, but I know with functions you can definitely do it. You can declare it like this in the header, and then here's a definition in the C file or CPP, and you can label it extern, but you can also not make it extern and it still works. So I wonder what the difference is here. Extern, void, use it. Function declaration headers for consistency to match the external and front of variable declarations and headers. Both C99 and require functions to be declared or defined before they are used. In front of function and headers for consistency to match the external and front of variable declarations and headers. Many people prefer to not use external in front of function declarations. The compiler doesn't care. And ultimately, neither do I, as long as you're consistent, at least within the source file. Okay, so extern in front of a function does nothing. Then why have it? Okay, so if I understand correctly, extern is very much necessary for variables, but it's optional on functions. But then why is it a thing on functions? I don't understand this inconsistency. It's strange. A source file never contains external declaration on variables. Yeah. Source files always include the header that declares them. Yeah. Header file only contains external declarations of variable, never static. A function should never need to declare a variable using external. Yeah. Avoid global variables. Okay. Let's get back here. Where were we? This technique localizes the variable definition to one file while still allowing access to that variable from other files. Yeah. You can also get tentative definition symbols when you accidentally import the same header file twice. To make sure you do not do this, include preprocessor directives to prohibit. Yeah. Analyzing MachO executables. You have several tools at your disposal for finding out how much memory your non-constant data is occupying. These tools report on various aspects of data usage. While your application or framework is running, use the size and page stuff tools to see how big your various data sections are and which symbols they contain. Some things to look for include the following. Okay, blah, we don't care. Okay. Minimizing your exported symbols. Identifying exported symbols. Okay, if your application or framework has a public interface, you should limit your exported symbols to those required for your interface. Exported symbols take up space in your executable file and should be minimized when possible. Not only does this reduce the size of your executable, it also reduces the amount of work done by the dynamic linker. Okay. By default, Xcode exports all symbols from your projects. By default, exports all symbols from your project, and which is good. Which is good. Because then when game publishers and developers ship their game, then we have access to the symbols. You can use the information that follows to identify and eliminate those symbols you do not want to export. Identifying exported symbols. Okay, explain something about this tool. External. Okay. Okay, I don't care. Good. I think that's about it here. Okay, what about this document here? Let's see. Okay, so let's see. What is this here? Throughout Cocoa. What is that? Cocoa. Is this some documentation for some framework? Okay. Okay, I don't know how this is any useful for us, yeah. I don't know what this stuff here is. Let's go back here once more. Runtime architecture. Let's search for it once more. MachO runtime architecture. Okay. 2004. Okay, well, it's about the time frame of the game. Hold on. Isn't there let's open here folder. Here, file info. So this is Xcode 10.4. 10.4. This says 10.3, but I don't know if these relate to the same thing. So this is Mac OS version. But this one is SDK. But maybe it refers to the same thing. So maybe this is appropriate document. Yeah, MachO runtime. Okay, let's download this document. MachO runtime. Let's put it here into our projects, assembly armada, MISC, MachO runtime. There we go. Okay, it's 92 pages. Let's make it a bit larger here. Okay, Apple computer, blah, blah, contents. Who should read this document? Blah, blah. Finding imported symbols. Okay. Data types, data alignment, stack structure, red zone. Position independent code. Oof. Okay, let's actually look through the sections here. Which ones could be of a special interest? Building and running MachO files. Okay, we don't care. Type of MachO files. Okay. Smallest unit of code. Static archives. Launching, forking. Finding imported symbols. Scope and treatment of symbol definitions. Yeah, this could be interesting. Loading code and runtime. Yeah, I don't know about this. Yeah, this one, I don't know. Data types, I don't know. Stack structure, no. Routine calls, no. No. Dynamic code generation. I don't know about these things. MachO types and data structures. MachO header, yeah. Yeah, this one looks interesting. Symbol table and related data structures. This looks very interesting, yeah. Relocation data structures, static. Okay, yeah, this stuff here looks interesting. We should look at that. And that's it. It comes at the end, but it takes a lot of pages here. Yeah. Okay, let's scroll through it and see what is especially interesting here. Okay, OS X supports a number of application environments, each with its own runtime rules. The only executable format the OS X kernel reads directly is a MachO file format, which gives MachO runtime architecture its name. And Mac OS X kernel extensions, command line tools, applications, frameworks, and libraries shared and static are implemented using MachO files. So there's a classic that runs Mac OS 9 within its address space and provides bridging services that allow Mac OS X to interact with Mac OS 9. Both classic 68K applications and PowerPC Code Fragments Manager can run under Mac OS 9 and Classic. Mac OS does not support the 68K variant of Code Fragment Manager, so you cannot run CFM, whatever. Launch CFM apps, command line tool that runs programs created for the PowerPC Code Fragment Manager. The file format used by such programs is called Preferred Executable Format. Carbon provides bridging for Code Fragment Manager applications that allows them to link to MachO base code. But for ease of debugging, if for no other reason, it's generally a good idea to use MachO for Carbon applications. Hotspot Java, we don't care. Kernel supports kernel extensions, static MachO executable files that are loaded directly into the address space of the kernel. Okay, that's not probably not used by games because errant code can write directly to memory used by the kernel. Kernel extensions have the potential to crash the operating system. And so this is more for drivers. Yeah. Blah, 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 we don't care. Okay, who should read this document? If you write development tools for the Mac OS, you need to understand the information presented in this document. Documentation is also useful for developers of shared libraries and frameworks and for developers of applications that need to load code at runtime. Overview of the runtime architecture, page 11. Describe the basics of the macOS runtime architecture, including detailed conceptual information about how macO executable files are built, linked, and executed. This chapter also explains how dynamic linking works with shared libraries, frameworks, bundles, and plugins. All programmers who create shared libraries or who dynamically load code at runtime should read this chapter. Describes a macOS X library binary interface for PowerPC microprocessors, which specifies low-level routine, calling conventions and data formats. Writers of assembly language code and authors of developers tools should read this chapter. MachO file format is probably the most interesting for us. Describes the layout of the MachO file format used for executables, shared libraries, bundles, and all other native executable machine code in the MachO runtime. Authors of developer tools should read this chapter. Okay. The runtime environment of the macOS X kernel, Darwin. See Darwin documentation. Okay. Oh, we saw Darwin actually mentioned yesterday in the tour. Darwin. I didn't know that this is the name of the kernel of OS X. Okay. I see. Okay. The macOS X compiler for the C, C++, and Objective-C language based on the GNU compiler collection, blah, blah. This is standard compiler. macOS GCC, macOS compiler for this based on GNU version this. This is standard compiler for macOS version 10.1. So this one says, well, there is a mention of 10.1 and 10.4. What is it then? Why are there 2 or 3? That's strange. CC tools. MachO static linker, dynamic linker, and related tools for examining and manipulating MachO files and static archive libraries. Linkers and loaders, blah blah. App compute, runtime architectures. Documents a classic segment loader architecture. Okay, I think that's not relevant for us. Okay. I don't know why they have empty pages here to make the document bigger. Okay, this chapter discusses how you use MachO runtime architecture. Describes the types of programs you can build, how programs are loaded and executed, the ways in which you can change the way programs are loaded and executed, how to load code in runtime, and how to load and link code at runtime. If you create or load bundles, shared libraries, or frameworks, probably want to read and understand everything in this chapter. I don't think we care. I don't think we care about this. Because we don't build, we don't link, we don't do that. Yeah. But maybe it's still good to have like a little bit of an understanding. To perform the work of actually loading and binding a program at runtime, the kernel uses a dynamic linker, a special marked dynamics shared library located at this location. The kernel loads the dynamic linker into a new process and executes it. Then a dynamic linker loads the program and all the frameworks and shared libraries that the program uses. A compiler is a tool. Static linker. Xcode tools, CD contains command line tools. Okay. Compiler driver contains compiling, assembling, and linking modules of source code. The compiler driver calls several other tools that implement the actual compiling, assembling, and static linking functionality. Actual compiler tools for each language dialect are normally hidden from view by the compiler driver. The rows transform input source code into assembly language for input to the assembler. Compiler driver links C++ runtime functions into the output file. Assembler, intermediate object files from assembly language code. It is primarily used by the compiler driver. Static linker is used by the compiler driver to combine MachO executable files. You can use a static linker to bind programs either statically or dynamically. Statically bound programs are complete systems in and of themselves. They cannot make calls other than system calls to frameworks or shared libraries. The macOS X kernel extensions are statically bound, while all other program types are dynamically bound. Even traditional Unix and BSD command line tools, all calls to the macOS kernel by programs outside the kernel are made through shared libraries, and only dynamically bound programs can access shared libraries. libtool creates static archives libraries or dynamic shared libraries. Blah blah. Okay. libtool blah blah. Tools for analyzing. MachO file analyzer. O-tool lists the contents of specific sections and segments within a MachO file. It includes symbolic disassemblers. Symbolic disassemblers. Okay, for each supported CPU architecture, and it knows how to format the content of many common section types. Lists the contents of specific section and segments. Symbolic disassemblers. I wonder if we find some like implementations of lookups in these two tools. Yeah. How about take a copy of this, put it here into some documents. To do check if these two tools contain any useful references. Got some spam here. What's the difference between W3D file and obsolete? Obsolete exists just to have a record of what existed once. If it's spelled obsolete, then that's a typo. Game has code here and there to either handle conversion of old data or report it's not supported, so the file is needed for. What? Got some spam here. Your ChatGPT more or less dismisses LLDB, but my Claude Sonnet seems more optimistic about it. Let's see. Okay, well, this begins with Python. That's not a good start. Get virtual methods. Module types. Get base classes. Get methods, get fields, has vtable. Okay, I mean, if it can get such information, can you test it? And is this also available? Probably. Can you test it? And I assume it's all in C++ too. Okay, let's keep on reading here. So the products, intermediate. Let's start from here. A typical application executes code that originates from many files. All these types of file contain code that conforms to the MachO file format and runtime calling conventions. The main executable file usually contains the core logic of the program, including the entry point main function. The primary functionality of a program is usually implemented in the main executables files code. See executing MachO files for details. Other MachO files containing executable code include intermediate object files are not final products. That's why they're called intermediate. They are the basic building blocks of larger MachO files. Usually a compiler creates one intermediate object file on output for the code and data generated from each input source file. You can then use a static linker to combine the object file into dynamic linkers. Integrated development environments such as Xcode usually hide this level of detail, and some development tools may not use a MachO format to store intermediate code and data. Dynamic shared libraries files and contain models and reusable executable code that your application references dynamically and that are loaded by the dynamic linker when this application is launched. Frameworks, umbrella frameworks, static archives, we don't care, bundles. Actually, executable file can load at runtime using dynamic linking functions. For virtual. Okay. Okay. To function properly in macOS, all MachO files except kernel extension must be dynamically bound. That is, built with code that allows dynamic references to shared libraries. By default, the static linker searches for frameworks and umbrella frameworks in frameworks, and for shared libraries, static archive libraries in lib. Okay. Modules. At the highest level, you can view a MachO shared library as a collection of modules. A module is the smallest unit of machine code and data that can be linked independently of the other units of code. Usually, a module is an object file generated by compiling a single source file. For example, given the source files main C, thing C, and foo C, the compiler might generate the MachO object files main O, thing O, foo O. Each of these output object files is one module. And the static linker is used to combine all three files into the dynamic shared library. Each of the object files is retained as an individual unit of code and data. Okay. When linking applications and bundles, the static linker always combines all the object files into one module. So I wonder if, like, I know that there are .os in the symbol table. I wonder if these also maybe give conclusions on where source files would have been, right? Yeah, but it doesn't make any statements about a header, so basically it's like the C file includes header files, so these object files probably also contain information from the headers. Yeah, I don't know. Individual, when linking applications and bundles, the static linker always combines all the object files into one module. Static linker can also reduce several input modules into a single module. Static linker can reduce several input modules into a single module. Okay, when building most dynamic shared libraries, it's usually a good idea to do this before creating the final shared library, because function calls between modules are subject to a small amount of additional overhead. Okay. AR commands. Okay, well, good job naming it the same. Okay, let's see. In addition to MachO files, the static linker and other development tools accept static archive libraries as input. You might use a static archive library to distribute a set of modules that you do not want to include in a shared library, but that you want to make available to multiple programs. Although an AR archive can contain any type of file, the typical purpose is to group several object files together with a table of contents, forming a static archive library. The static linker can link the object file stored in a static archive library into a MachO executable or dynamic library. Note that you must use the libtool command to create the static library table of contents before an archive can be used as a static archive library. Okay, we don't care. Executing. Dynamic loading process. Process of loading and linking a program mainly involves two entities, macOS kernel and dynamic linker. When you execute a program, the kernel creates a process for the program, then loads and executes the dynamic linker shared library in the program's address space. The dynamic linker then loads the program and the libraries it references. This process is described in detail next section. It's the same stuff that happens on Windows as well. Launching, forking, system calls you can use. Okay, how dynamic linker sets up the program's runtime. How dynamic linker links to imported symbols of a file. Okay. When you launch an application from the Finder or the dock, or when you run a program in a shell, the system ultimately calls two functions on your ball, fork and exec. Creates a process, loads and executes a program. There are several variants exec functions, such as exel, exec l, exec v, blah blah, blah 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 blah. Okay, we don't care. We don't care. We also don't care about this. Finding imported symbols. When the dynamic linker loads a MachO file, which the purpose of the section is called a client program, it connects the file's imported symbols to their definitions in a shared library or framework. The settings used to build the client program affects this process as explained in the following sections. Binding symbols. Describe the process of binding the imported symbols in one MachO file to their definitions in other MachO files. Static linker allows you to specify a number of different ways to perform the binding process. Searching for symbols. For each imported symbol the dynamic linker finds, it uses this process to determine the location of the symbol. Binding symbol. I think we don't really care about this. Blah blah, yeah. It's details about how the symbols imports, exports. Well, let's read this one. A symbol is a generic representation of the location of a function, data variable, or constant in an executable file. References to functions and data in a program are references to symbols. Reference to functions and data in a program are references to symbols. Yeah. To refer to refer to a symbol when using a dynamic linking routines, you usually pass a name of the symbol, although some functions also accept a number representing the ordering of the symbol in the executable file. The name of a symbol representing a function that conforms to standard C calling conventions is the name of the function with an underscore prefix. Thus, the name of the symbol representing the function main would be underscore main. Programs created by the Mac OS X development tools and all symbols from all loaded shared libraries into a single global list. Any symbol that a program references can be located in any shared library as long as that shared library is one of the program's dependent libraries, or one of the dependent libraries of the dependent libraries. Chaining of libraries. Mac OS X version 10.1 introduced a 2-level simple namespace feature. Okay, the first level of the 2-level namespace is the name of the library that contains a symbol, and the second is the name of the symbol. Okay, 2-level simple namespace feature. Have we seen this in symbols? I don't think so. I haven't seen this kind of thing. With the 2-level namespace enabled, when the static linker records references to imported symbols, it records a reference to the name of the library that contains the symbol and the name of the symbol. Linking your programs with 2-level namespace feature offers two benefits over the flat namespace. Enhanced performance when searching for symbols. Forward compatibility. Flat name 2 or more libraries cannot contain symbols with different implementations that share the same name. Link directly, blah blah. Okay. For programs that do not have a 2-level namespace, you can tell the linker to define references to undefined symbols, even if the linker cannot find the library that contains them. When you build an executable with such undefined symbols, you are making the assumption that one of the other files loaded as part of the executable file at runtime contains those symbols. Bundles and shared libraries sometimes use this option to reference symbols defined in the main executable. However, this causes you to lose the performance and compatibility benefits of two level namespaces. It's usually better to explicitly link against an executable that defines the references. However, if you must link with undefined references, you can do it by enabling the flat namespace feature and suppressing undefined reference warnings using the option flat namespace undefined suppress. Blah, blah, blah. Okay. Okay, blah, we don't care. Treatment, blah, okay. Undefined external is any symbol defined in the current MachO file, including function and data. Following C code defines an external symbol. And X defines, okay? So this would be in a CPP file, and this would be in the header file. Following C code defines two external symbols, a variable and a function. Yes. Okay. A common symbol is a symbol that may appear in multiple intermediate object files. Static linker permits multiple common symbol definitions with the same name in input files and copies the one with the largest size to the final product. If there's another symbol with the same name as a common symbol, a static linker ignores the common symbol instead. Tentative definition, a global variable that has no initializer and is not marked extern. The following line is an example of a tentative definition, int x. A shared library cannot have common symbols. To eliminate common symbols in an existing shared library, you must either explicitly define the symbol with an initialized value, for example, in one of the modules of the shared library, or pass no common flag to the compiler. Private symbol. Not visible to other modules. Okay, actually, let's pay attention here. A private defined symbol is a symbol that is not visible to other modules. So this one is not visible to other modules. Static int x, which means it must be in a CPP file, I think, or a C file. A private external symbol is defined external symbol that is visible only to other modules within the same MachO file as a module set contains it. The standard static linker changes private external symbols into private defined symbols unless you specify otherwise. Okay, I've never heard about this before. You can mark a symbol as private external by using a private extern. Which works only in C. Okay, then we don't care. A weak reference is an undefined external symbol. Undefined external symbol that need to be found in order for the client program to successfully link. Weak reference. If the symbol does not exist, the dynamic linker sets the address of the symbol to 0. Files with weak references can only be used in macOS that and later. The following C code demonstrates conditionalizing an API call using a weak reference. Only call this API if it exists. Summary function is not null. Summary function. Okay. To specify that a function should be treated as a weak reference, you should use a weak import attribute. Okay. Weak import. Okay. I also have never seen this before. So basically, it allows you to link to a function, but it's optional. That's the way I understand it. Yeah. Okay, that's interesting. Yeah. But why? What would that be useful for? Plugins? I don't know. A coalesced. How's this pronounced? Coalesced. Coalesced, maybe. Coalesced symbol. A coalesced symbol is a symbol that may be defined in multiple object files. Multiple object files. But that the static linker generates only one copy of in the output file. This can save a lot of memory with certain C++ language features that the compiler must generate for each individual object file, such as virtual function tables, runtime type information, and C++ template instantiations. The compiler determines which constructs should be coalesced. No work on your part is required. Programmers who use other operating systems may be familiar with the concept of symbols that are marked with a comdat flag. A coalesced symbol is a MachO equivalent feature. I have never heard of comdat. Weak definition is a symbol that is ignored by the linker if an otherwise identical but non-weak definition exists. This is used by the standard C++ compiler to support C++ template instantiations. The compiler marks implicit and not explicit template instantiations as weak definitions. A static linker that then prefers any explicit template instantiations to an implicit one for the same number. I'm confused. Which provides correct C++ linking. I'm confused by this. Debugging symbol is a symbol generated by the compiler that allows the debugger to map from addresses in machine code to locations in source code. I don't think that we have debugging symbols in our MachO file. The standard compiler currently generates debugging symbols in the stabs debugging format, which is documented in the GDB debugger. Stabs. Okay. Debugging symbols, like other symbols, are stored in a symbol table. This section describes how we can load code at runtime. Oof, do we care? I don't think so. We don't care about that. Let's scroll over this. Love.c, peace.c. Great names. We don't care. We don't care. We don't care. Runtime conventions. Cover specific low-level details of the macOS PowerPC runtime architecture. Together, these details specify the MachO PowerPC application binary interface. If you are writing PowerPC assembly code or creating macOS development tools, you should understand and conform to these conventions to ensure compatibility with the other programs running in the MachO runtime architecture. Okay, scalar types, yeah. So a long is 4, same on Windows. Unsigned long is also same on Windows. Underscore bool, I think that's only C. It's not C++. Yeah. Which is strange why C has this bool thingy. Yeah. Okay. Yeah, nothing out of the ordinary, I would say. That didn't list float here. Oh, there we go. Float, double, yeah, long, double. C notes below. Pointer 4. Okay, that's for 32-bit. Vector. Okay. I never seen vector before. Vector data types. Huh. Okay. Never seen this before. I don't know if we care. As in most architectures, a byte is 8 bits long, that's 1 byte, and a null pointer has a value of 0. All floating point conform to IEEE 754. PowerPC processors use a big endian format to store numeric and pointer data types. Big endian. I think Windows uses little endian. Most significant bytes first, and then least significant bytes. Yeah. PowerPC processors use 2's complement binary representation for signed integer types. Okay, I don't know what that means. 2 complement binary? 2's complement binary representations. So hexadecimal or what? I don't understand. On 32-bit PowerPC processors, arithmetic for 64-bit integer data types long must be implemented by the compiler. Since the CPU itself does not implement 64-bit integer mass operations. Long double extended precision type is 16 bytes. That's plenty on classic Mac OS. But for PowerPC, it treats it as 8 bytes. Equivalent to double. A future revision of the compiler may extend long double to this. Okay. For this reason, it is not currently recommended. Long double. Vector types are available only on CPUs that implement altivec execution unit. I don't know if that's still a thing then. I've never heard of altivec. I don't know what that is. Maybe it was just like a short thing during the 2004s on Macintosh, but I never heard this. PowerPC runtime environment supports multiple data alignment modes. Alignment of data types from 2 category national alignment. And embedding alignment, which is the alignment of data type within a composite data structure. For example, the alignment of an unsigned short variable on the stack may differ from that of an unsigned short data embedded into the data structure. Blah, 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 blah. Blah, 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 blah. I don't think we need to care much about alignment here. Power alignment mode. Yeah, we don't care. Yeah. We don't care. We don't care. So char 1, 2, 4. Underscore bool is 4 bytes. No, it's just the. Maybe it's 1 byte, but it's 4 byte alignment. That's weird. Really weird. Okay, you can change alignment, blah. Stack structure. PowerPC runtime environment uses a grow down stack that contains linkage information, local variables, and routines parameter information. Stack before calling a procedure. Parameter area, linkage area, stack grows down. Stack after calling procedure. Saved registers, local variables, parameter area, linkage area. Stack pointer. Stack convention, use only a stack pointer, held and register, blah, and no frame pointer. Okay, do we care much about all this? It's more for runtime. Prologues and epilogues. Call routine is responsible for allocating its own stack frame. Okay, it's the same on Windows. The cdecal calling convention. Making sure to preserve 16-byte alignment on the stack. This action is accomplished by a section of code called a prologue, which the compiler places before the body of a routine, aka a function. After the body of the routine, the compiler generates an epilogue to restore the processor to the state it was prior to the prologue. Yeah, it's the same on Windows executable. Decrement stack pointer account for the new stack frame. blah. Okay. We don't care. We don't care. Red zone. Space beneath the stack pointer where a new stack frame would normally be allocated is called the red zone. Red zone. This area, maybe it's funny. Okay, we don't care. The red zone. Yeah, okay, we don't care. Routine calls, blah, blah. Yeah. A variable argument routine may have several required fixed parameters preceding the variable parameter portion. For example, int number ... Gives no restriction on the number of arguments after number, but you precede them with a number argument. Therefore, number is a fixed parameter. Typically, the calling routine passes parameters and registers. However, the compiler generates a parameter area and the caller stack frame that is large enough to hold all parameters passed to the called routine, regardless of how many of the parameters are actually passed in registers. There are several reasons. Okay, we don't care. We don't care. We don't care. It's all runtime implications. We don't care. Return type, PowerPC runtime functions return floating point values and register. Other values are returned as follow. We don't care. Okay. What is this? Dynamic code generation. To support dynamically bound shared libraries, applications bundles, compiler tools, and the dynamic linker support features position independent code and indirect addressing. Position independent code is the name of the code generation technique that allows the dynamic linker to load a region of code at a different virtual memory addresses. Without some form of position independent code generation, the operating system would need to place all code you wanted to be shared at fixed addresses, and of course we don't want that. It should make maintenance of the operating system remarkably difficult. For example, it would be nearly impossible to support shared libraries and frameworks because each one would need to be pre-assigned an address that could never change. Yeah. MachO position independent code, the same on Windows. It's based on the observation that the data segment is always located at a constant offset from the text segment. That is, a dynamic linker, when loading any MachO file, never moves a file's text segment. Never moves a file's text segment relative to its data segment. Therefore, a function can use its own current address plus a fixed offset to determine the location of the data it wishes to access. All segments of a MachO file are at fixed offsets relative to the other segments. If you are familiar with the executable and linking format, ELF, you may know that MachO position independent code is similar to the GOT, Global Offset Table Scheme. The primary difference is that MachO code references data using a direct offset, while ELF indirects all data accessed through the global offset table. Position independent code is typically required for shared libraries and bundles to allow the dynamic linker to relocate them to different addresses at load time. But we don't care. For our purposes, we don't care about the runtime. So relocation, we don't care. However, it is not required for applications that typically reside at the same address in virtual memory. Apple's version of GCC introduced a new option called that to reduce the code size. Blah, blah. Position independent code generated for the C code source code example for position independent codes. Yeah, I mean, it's just a definition of a struct, and this is a struct definition with some contents. And for return bar dot member2 bar dot member2 Yeah, I don't think we need to go in detail of this one. It's more about the runtime. We don't care. Yeah. Okay. Okay, but here the interesting stuff should start. MachO file format reference. This chapter describes the structure of the MachO executable file format, which is the standard used to store programs on disk in the MachO runtime architecture. To understand how the Xcode tools work with MachO files and to perform low-level debugging tasks, you need to understand this information. Okay, a MachO file contains 3 major regions. At the beginning of every MachO file is a header structure that identifies a file as a MachO executable file. The header also contains other basic file information. It indicates the target CPU architecture and contains flags specifying options that affect the interpretation of the rest of the file. Directly following the header are a series of variable size load commands that specify the layout and linkage characteristics of the MachO file. Among other information, the load commands can specify initial layout of the file in virtual memory, location of the symbol table used for dynamic linking and debugging information, the initial execution state of the main thread of the program, the names of the shared libraries that contain definitions for the main executables, imported symbols. Following the load commands, all MachO files contain the data of one or more segments. Following the load commands, all MachO contain the data of one or more segments. Each segment contains 0 or more sections. Yeah. Each section of a segment contains code or data of some particular type. Each segment defines a region of virtual memory that the dynamic linker maps into the address space of the process. The exact number and layout of segments and sections is specified by the load commands and the file type. Exact number and the layout of segments. Okay. Let's see. Hello. Load commands, segment, and these guys contain the sections. Various tables within a MachO file refer to sections by number. Section numbering begins at 1, not 0, and continues across segment boundaries. Thus, the first segment in a file may contain sections 1 and 2, and the second segments may contain sections 3 and 4. Okay. So it would be, yeah, here it shows here 3 and then 4 in the next segment. A MachO file contains code and data for one CPU architecture. The header structure of a MachO file specifies the target CPU architecture or multiples in our case, which allows the kernel to ensure that, for example, binary machine code intended for PowerPC processors is not executed on an x86 processor. You can store MachO files for multiple CPU architecture in one file using the format described in multi-CPU architectures. Yeah, so the MachO file that we have targets the PowerPC, but also the Titanium 386, which is for x86 processor. So we are not So we are not concerned about PowerPC portion, but only about the Itanium portion, which actually makes me wonder, why is there a PowerPC in the first place? And does it reuse parts of the x86? It must be, because the PowerPC portion seems to be much smaller. Well, that's another discussion. Okay, segments and sections are normally accessed by name. Segments by convention are named using all uppercase letters preceded by 2 underscores. Yeah, we know this. Sections should be named using all lowercase letters preceded by 2 underscores. Text. This naming convention is standard, although not required for the tools to operate correctly. Okay. A segment defines a range of bytes in a MachO file and the addresses and memory protection attributes at which those bytes are mapped into virtual memory. When the dynamic linker loads the application as such, segments are always virtual memory page line. Segments that require more memory at runtime than they do at build time can specify a larger memory size than they actually have on disk. For example, the page is 0 segments generated by the linker for PowerPC executable files has a virtual memory size of 1 page, but on disk size, but an on disk size of 0. Because page 0 contains no data, there is no need for it to occupy any space in the executable file. Okay, but then why is this there? Page 0, I don't know. A segment contains 0 or more sections. For performance reasons, sections that are to be filled with zeros should always be placed at the end of the segment. Okay. For compactness, an intermediate object file contains only one segment. The segment has no name. It contains all the sections destined ultimately for different segments in the final MachO file. The data structures that defines a section contains the name of the segment the section is intended for, and the static linker places each section in the final MachO file accordingly. Okay. Oh boy. For best performance, segments should be aligned on virtual memory page boundaries. Yeah. And 8K for this. Okay. Calculate the size of segment, add up the size of each section, and round up to the sum of the next virtual memory page boundary. Using this algorithm, the minimum size of a segment is 4 kilobytes and thereafter size at 4 kilobyte increments. Header and load commands are considered part of the first segment for paging purposes. In an executable file, this generally means that the headers and load commands live at the start of the text segment because that is the first segment that contains data. Page 0 segment contains no data on this, so it's ignored for this purpose. Oh boy. Okay, do we care about this? I don't think so. Text segment contains executable code and other read-only data to allow the kernel to map it directly from the executable to shareable memory. The static linker sets this segment's virtual memory permissions to disallow writing. Makes sense. You don't want to tamper with the executable code. When the segment is mapped into memory, it can be shared among all processes interested in its contents. This is primarily used with frameworks, bundles, and shared libraries, but it is possible to run multiple copies of the same executable in MachO OS X, and this applies to this case as well. The read-only attributes also means that the pages that make up the text segments never need to be written back to disk. Yeah. When the kernel needs to free up physical memory, it can simply discard one or more text pages and reread them from disk when they are needed. Okay, but if you run so low on memory that you have to unload executable code, well, things will get slow. Yeah. The data segment contains writable data. Yeah. The static linker sets the virtual memory permissions of the segments to allow both reading and writing. Because it is writable, the data segment of a framework or other shared libraries is logically copied for each process linking with the library. When memory pages such as those making up the data segments are readable and writable, the kernel marks them copy on write. Therefore, when a process writes to one of these pages, that process receives its own private copy of the page. Makes sense. Because every runtime needs to have their own state, right? You cannot just share states between different processes. Unless you want them all to behave the same, but then why have different ones? Object C segment contains data used by Objective C. Okay, we don't care. Linked edit contains raw data used by the dynamic linker, such as symbol, string, and relocation table entries. Okay. Okay. Dynamic linker. Text and data segments may contain a number of standard sections listed in table 3.1. Executable machine code. The compiler places only executable code in the sections, no tables or data of any sort are stored here. Makes sense. We have already seen this, but let's go through it once more. Constant C strings. A C string is a sequence of null bytes that end with a null byte. So zero termination. Static linker coalesces constant C strings values, removing duplicates, then building the final product. That makes sense. Position independent indirect symbol stubs. We went over this, yeah. Or did we? I already forgot. Indirect symbol stubs. See indirect addressing for more information. Initialize constant variables. Compiler places all data declared const in this section. So this means also const variables in functions, no? Maybe. Probably. No, maybe not. I'm not sure. 4-byte literal values. Okay. The compiler places a single precision floating point constant in the section. Huh. The static linker coalesces these values, removing duplicates when building the final product. With some CPU architectures, it's more efficient for the compiler to use immediate load instructions rather than adding to the section. Yeah. And here's the same stuff for 8 bytes. Initialized mutable variables such as writable C strings and data arrays. There's a symbol pointer, placeholder section used by the dynamic linker, uninitialized constant variables. Huh. Why didn't they just why is this two? Oh, hold on. This is data. Right. So all data declared const in the section. Uninitialized constant variables. It's weird though. Why is an uninitialized constant variable? Why is it in the data section? I don't understand why it's here. I mean, you cannot write to it, so why is it part of data? Why is it? So data is writable, right? So why is this here? Shouldn't this be also part of text section, which is not writable? I don't understand why this is here. This makes sense, right? You have mutable variables. You want to change it. Static, uninitialized static variables, same thing, right? This, I don't understand why this is here. Imported symbol definitions. Data for uninitialized static variables. Okay. Yeah, okay. This section describes the data types that compose the MachO files. Data structures are written using the host CPU's byte ordering scheme, except for fat header, fat arc, which are written in big endian type byte order. All these data types can be found in loader.h. Okay. Specifies general attributes of the file. Mac header. Magic, CPU type, subtype, file type, size of sim, these flags. Okay. I think we don't care about this Mac header because leaf already takes care of this pretty much. Yeah. We don't care. Or do we? File type is the format used for intermediate object files. Very compact format containing all of its sections in one segment. The compiler and assembler usually create one MH object file for each source file. Okay. So this Mac header. So this Mac header is not just for the Mac file itself, but it's also for object files, the .o files, and they are embedded in this. And the executable, I don't know. Format used for intermediate object files. File name extension for the format is .o. So maybe I see. So I suspect that .o files also have this Mac header, and then it has this type here. And the type that we are looking at is probably this one, standard executable programs, and none of the others here. Okay, I see. Load commands, okay. Integer indicating the number of bytes occupied by the load commands following the header structure. Okay. Flags. We probably don't care. Don't care. Subsections via symbols. Sections of the object file can be divided into individual blocks. These blocks are dead stripped if they are not used by other code. Dead code stripping, okay. Okay, and then there are load commands. Load commands. There's a command size. Okay. Okay. So there's a command, segment command, but yeah, leaf already takes care about all of this, so we don't need to implement any of this. So there is a segment, yeah. There's a LC sim tab. Yeah. A thread. For an executable file, command defines the initial thread state of the main thread of the process. LC thread is similar to Unix thread, but does not cause the kernel to allocate a stack. Okay. Load dylib. Okay. Pre-bound dylib. Load then linker LC routines. Contains the offsets of the shared library initialization routine. Okay. 2-level hints. Okay. Okay, segment command has some, here's some information. Okay. Field descriptions. Yeah, we don't care. Section. Yeah, section. We don't care. Leaf also already takes care about this, I think. Well, let's see. Let's go to our sample program here. So we have segment and section here. Let's see. So we have name, segment name, we have offset, we have size. Let's go in here. Content entropy. Full name. It doesn't show a line here. That's missing. Yeah. Rel off. And relog address. It seems like this section, it doesn't give us all the information here. Maybe just important things. An abstracted section. Yeah. So to me, it looks like we lose some information here. Leaf doesn't give us everything. Yeah. I wonder if LLVM gives us more than that. Okay. How about we take a break? It has been quite a session already. Yeah, but we went quite far through the document, so that's good. But yeah, I think a break would be good. Yeah, let's continue reading in the next session. And yeah, I did it already talk about segments, by the way. Probably. So this was section. What about segments? Here, segments. Let me see this real quick though. Segments. Oh, hold on. Section. MachO section. Yeah, hold on. Segment command. Load command. Is there also a section command? No. But there is a segment command. Link edit, segment command. So it does has some more info here. Symbol command. Symbol offset, so number of symbols. Strings offset. Huh. Symbol table. Span. I would be nice to like take a good look at all the MachO stuff that is here. MachO binary. Let's take a look at this guy. So it has a header. Mm-hmm. 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 Commands. Load command. Mm-hmm. 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 It has the symbols, sections, segments, cache, sections, cache, section. Oh, look at that. There's more information. Isn't there? Ah, there's the alignment. Look at that. Why didn't we see that before? Hold on. Huh? Didn't we look at section before and there was a lot of stuff missing, but now this one looks more rich in information. Hmm. Looks like it has all the stuff. Mm-hmm. Okay, cool. Mm-hmm. 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 Sections cache. Segments cache. Let's look at this one. Segments command. Okay, we have seen this. This one also contains a lot of information. Yeah. Okay. Mm-hmm. Libraries cache, sections cache. Yeah, I think this one we don't really care about, the dilib command. Symbols. Yeah. So there's this symbol here. Which we already have seen. Yeah. There's also symbol commands here. Okay. Anyway, let's take a break here. So next session we read a bit further here. But yeah, to me, so there's a chance that everything this describes is basically just everything that Leaf already does. Maybe we won't get any more information out of this. It's certainly possible. Good. Yeah, we'll take a break here. I wish you a great day or night. Until next time. Goodbye.